In section 3.5, we're going to be talking about using quadratic functions in applications and particularly to model real-world situations. Our first example, a ball is thrown vertically upward with an initial velocity of 96 feet per second. The height, h, which is given in feet, of the ball up off the ground after t seconds is given by this quadratic function. H of t is 96t minus 16t squared. This problem we're going to do by hand, and then we'll do the next one with technology just to compare the techniques. We could verify this one with technology as well, but we'll at least work through it by hand first. So the first thing we'd like to know is what is the height of the ball after 2 seconds? Since t is the number of seconds, essentially we're being told here that t is 2. So if we just find h of 2, let's see, I'm just going to use my Desmos as my calculator again here. We get 128. And height is in feet. So at the 2-second mark, that ball is 128 feet off the ground. All right. Question B may seem like we already know the answer. It said at what time, but possibly times, is the ball exactly 128 feet above the ground? Now we saw already in part A that that happens at 2 seconds. But if you think about it, if you throw something up in the air and allow it to come back down, in actual fact, any particular height, like 128 feet, really it would make sense if there were 2 different times that that happened, once on the way up and once on the way down, right? So I'm expecting to get t equal 2, but I think I'm probably going to get a second time as well. Let's try it out. 128 feet is the height, so we're putting h equals 128. And so our equation looks like 128 equals 96t minus 16t squared. And by now, you guys all know my preference for positive leading coefficients. So I'm going to choose to move everything to the left side. That way I'm adding the 16t squared. And then I'll have a minus 96t plus the 128 that was already there. And that gets my quadratic function equal to 0. All right, in this case, I think these were actually kind of designed so that that 16 can be factored out. 96 divided by 16 is 6. And 128 divided by 16 is 8. So that was a setup, I think. All right, I think we can continue to factor here if we're looking for a sum of -6, a product of 8, -2 and -4. So I have my 16, and then this is now just a 1t squared. So I can take my little shortcut, t times t. I've got -2 and -4. All right, there's no variable factored out here, and 16 certainly does not equal 0, so I can pretty much ignore that. And just go to the t minus 2 equals 0, and t minus 4 equals 0. So we do get 2 seconds like we expected, but then we also get 4 seconds. So it must be on the way up. This happened at 2 seconds, and then on the way back down it must have happened at 4 seconds. All right, the next question was to find the zeros of h of t. Remember, the zeros of the function, you're just finding the values that make the function equal 0. So in this case, I'm putting the function h of t itself equal to 0. And I think I'll try to solve this one by factoring as well. We already know we can factor out a 16. And then in this case, I can factor out t also. It's going to give me a 6 there, minus 1t there. So 16t equals 0. Notice this time there is a variable factored out, so I had to account for that. Here it was just a 16, so I didn't have to worry about it. And then 6 minus t equals 0. This would say t equals 0, and that would say t equals 6. As far as what they mean, what I really did when I set my function equal to 0 was I was saying the height was 0. Or in other words, the ball is on the ground, right? It has no height. Totally makes sense here. At the beginning, before we threw the ball up in the air at all, it was on the ground. And this must mean that it lands back on the ground again after 6 seconds. So the ball starts. At height 0 feet. That's the t equals 0. And then lands at 6 seconds back on the ground. All right, the last question about this problem, what is the highest point reached by the ball? And how long does it take the ball to reach this point? I'm just going to rewrite my function here. Without going into a lot of details, what can you tell me about the graph of this function? It's quadratic, so it would be a parabola, right? And if I wrote it in descending order, like we're typically used to seeing it, notice that I have a negative leading coefficient. So a parabola with a negative leading coefficient is going to be a parabola that opens downward, right? And that means the highest point, the maximum height, is really just asking me for the vertex of that graph. The t value of the vertex will be how long it takes, and then the h value of the vertex will be the actual highest point. So this problem comes down to finding the vertex. Now we do know how to do that by hand, right? This is in expanded form, so I'm thinking we should use that, in this case, t rather than x, but equals minus b over 2a, that vertex formula. Minus b would be negative 96 over 2 times negative 16. Negative 96 divided by negative 32 gives me t equals 3. I can plug that 3 back into my function to find the h value. And let's see, get a little bit of help from my calculator again. It's 144. So, the ball reaches the highest or maximum height of 144 feet at the 3-second mark. So at 3 seconds, the ball reaches its maximum height of 144 feet. And this is really typical of quadratic modeling problems. Since every parabola has a vertex, which is either a maximum or a minimum if the parabola is opening up. When you're asked about the highest or lowest or most or least, typically with a parabola, what you're really being asked to do is find the vertex. All right, I'm going to go ahead and graph this height function, and let's just see if we can probably really quickly verify all of our answers here. So my height function was 96t minus 16t squared. And I definitely need to look a bit higher on the y direction, or each direction. There we go. All right. The first thing we're supposed to do is find h of 2, which I can type right into Desmos. That was that height of 128 feet. And indeed, that's exactly what we got. The second question was, at what times are we 128 feet up? So if I just add the y equals 128 to my graph, notice here we are on the way up. At 2 seconds, the height is 128. And here we are on the way down. At 4 seconds, the height is 128. We wanted the zeros here and here. 0 seconds when we first throw the ball up in the air, and 6 seconds the height is back at 0 on the ground. And then the highest point, the vertex, there we are at 3 seconds and 144 feet. So a graphical approach to this problem actually goes really quickly and smoothly. All right, let's try another one. As I said, in that one, I think the numbers were kind of engineered to make the problem relatively straightforward by hand, but most real-world problems, that is not the case. So technology becomes even more important to avoid spending a ton of time crunching numbers. Here's a good example of that. In the US, the birth rate B for unmarried women, that is births per 1,000 unmarried women, at age A can be modeled by this function, B of A. It says use technology to help this time, so we get to use our graph. We're going to answer these questions. So, let me first of all just graph my function. B of A, negative 0.31a squared, plus 116.54, okay, minus 151.04. All right, and we need to get our graph a bit better here, showing what we want to show. There, that's not bad. All right, so I've got my graph, and the first question was, what is the birth rate for unmarried 20-year-old women? Well, my input here is the age, A, so all I really want to do is find B of 20. And it's about 55.76. So when I found B of 20, 55.76. And just a reminder, that would mean that there were just about 56 births per 1,000 unmarried 20-year-old women. So it's not a percentage. That would be a really high percentage, right? It's not per 100, it's per 1,000. All right, the next question. This time we want to find the age. We want to find A so that B of A equals 35, and then we'll talk about what that means. So this time I want the B value to be 35. I'm looking for 35, which is somewhere right about in here. You can see it's going to happen a couple of times. The easiest way to pinpoint that location is to add the line y equals 35 to my graph, and then I can locate exactly where we're at. So it looks like the inputs, the A values, would be approximately 16 and again approximately 37. A, remember, stands for age, so it kind of makes sense to round these off to nearest whole numbers. So I'm going to go with 16 and 37. We have the output of 35. All right, those are ages. So birth rate is 35 per thousand. There are about 35 births per thousand. Unmarried women of age 16, and again at 37. All right, next question. Find the zeros and explain what they mean. The zeros, the x-intercepts, right? I'm going to get rid of this line because we don't really need it. So my x-intercepts or zeros are here and here. And again, I'm going to round those to the nearest year for age. So I'm going to say the first one's about 12 and the second one's about 42. And again, you can see the output there of 0. So these would be ages at which there would be no births per thousand or per any unmarried women. So no births to unmarried women. Of age 12 and 42. And you know, it seems reasonable, right? I mean, that's a bit on the young side. 42, most women are kind of getting past it. And maybe not. It may not be absolutely none, but we're down to such a small number that it's probably not showing up statistically. That seems like reasonable limits for that. All right, and then the last question. At what age is the birth rate for unmarried women at its highest? And what is that birth rate? So highest, as soon as I see that, I'm thinking vertex. My vertex is right there. The vertex is 26.7, 69.6, roughly. And remember, this is an age, and this would be the birth rate B. So the maximum birth rate amongst unmarried women is about 70 births per thousand, and that's going to occur at approximately age 27 if I round that off to the nearest age. Maximum birth rate. Among unmarried women is about 70 births per thousand. At approximately age 27. All right, so again, that one would have been a much more difficult problem if we had to struggle through all the numbers algebraically on paper, with the numbers being not nearly as friendly as they were in the first problem. But with the calculator, Desmos, it makes it much easier. All right, we have one more where we pretty much give you the equation, and then we'll look at a couple of models where we have to find the equation ourselves. So in example 3, we're talking about a problem in economics. It says the revenue from the sales of a particular item is the number sold, N, multiplied by the price of each item, P. And that gives us this revenue equation, R equals N times P. Hopefully that seems pretty logical, right? Your revenue, or how much money you take in, is how many do you sell times the price for each one. Now there's also a relationship between the number sold and the price. This is called the demand equation. And the demand equation is going to vary depending on the product. But notice the demand equation logically should also depend on price, right? In general, if you price something lower, you're probably going to sell more. You price something higher, you're going to sell less. So it would make sense that the demand equation should also depend on price. All right, in this particular problem, it tells us that market research for a particular brand of phone shows that at price P, the number of phones sold in thousands will be n equals 800 minus 2.5 P. So notice there it is, the number sold does depend on the price. As P gets bigger, we're subtracting more, so n, the number sold, would go down. All right, what is the slope of the demand equation? My slope here is negative 2.5. And let's see, the output was n, the number sold. So I'd say the number sold is decreasing. By this much, 2.5, and that would be in thousands. So 2.5 thousand. Or you could write that as 2,500. Per, let's see, I would assume this would be in dollars, so I would assume that that would be per dollar increase in price. So the question is, how many phones could we expect to sell if they're priced at $250? So the price is $250, n would then be 800 minus 2.5 times 250. And let's just do the arithmetic here. That's 175. And remember, the n is in thousands. So I could write that as 175,000 phones would be the expected sales if we put a $250 price tag on them. All right, the next question was to find the revenue as a function of price, R of P. And remember, we had a revenue equation up here. Revenue is n times P. But I want this as a function of just price. I don't want the n variable in there. So I'm going to go ahead and I'm going to take my n equation and I'm going to substitute it for the n here. So I'll replace the n with 800 minus 2.5p multiplied by that p right there. And I could multiply that out. I would have 800p minus 2.5p squared. And notice now the only input variable is p, so this is truly the function R of p. Okay, we are now being asked to fill in the table of values that shows the revenue based on various prices of selling these phones. So to make my life a little bit easier, I could do R of 50, R of 100, R of 150, whatever. We haven't used a table for this for a little while, so that might be a good skill to review. I'm going to put in my R equation, and then I'm going to make a table to do this for me. So let's start by defining our function r of p, which was 800p minus 2.5 p squared. I've got a graph over here. I'm not going to worry about it because right now I really just want a table. So for each price, P1, that I input, I would like R of P1 to be my output. And starting at a price of 0, it would make sense that my revenue would be 0, right? If I'm not charging anything, I'm not going to make any money. 50 was actually the first price listed in the table, I guess. So $50, our revenue is going to be a little under $34,000. At $100, we're going to bring in $55,000. $150, $200, $250, and $300. So you can kind of see in this table, can you see the revenues getting bigger and bigger, and then they start coming down smaller and smaller. So this increases for a while and then decreases. Typical behavior for a parabola, right? It both increases and decreases. I'm just going to jot those down so we can talk about them a little bit more. So 33,750 and so on. All right, so there are the values for the specific prices that we were asked to find. So the next question is, how should the price be set in order to maximize the revenue? Now, be careful with that question, because if you're just looking at the table numerically, you might kind of automatically go to that $150 because it does have the largest revenue on the table. But notice we haven't tried every single possible price, right? I mean, maybe it's actually $155, or maybe it's $190, right? Or maybe it's a little bit less. Maybe it's $140. We don't really know that that's going to be the largest revenue. It's just the largest for the prices that they picked. So we shouldn't go by the table on this. We should definitely use the graph. Our function is once again a parabola opening down. Notice that negative leading coefficient. So what I'm really being asked to find here is the vertex, right? I want to maximize the revenue. So I'm going to go back to the graph, and this time I am going to go ahead and try to find something that's going to show up. Get a little better. There we go. Oops, had it and then I lost it. There we go. All right, I'm going to turn off the individual points so they're not distracting me. And now I can look for the vertex. Looks like it's $160, right? The vertex was 160, comma 64,000. And so we should set the price at $160. To maximize revenue at $64,000. All right, so we had to do a little bit more to get our equation that time, but basically they still gave us everything that we needed. If they don't give me an equation, if instead they just give me the data, then I'm going to have to go back to that regression idea. We've done this with linear models, and you're going to see a very similar technique that we're now going to use with quadratic models. So these problems, we're going to have to build the model ourselves from data. Okay. Quick note, You know that a line is determined by 2 points. So if we had 2 points, we could always find the equation of a line that contained them. For a quadratic model, we do need a minimum of at least 3 data points to get a quadratic model. Usually, we'll have more than that, but minimum of 3. Right? Unlike the linear equations where we learned how to do them by hand, we're always going to use regression for quadratic models. So no worries about doing these by hand, definitely regression with Desmos. In example 4, this table shows us the average fuel economy, m miles per gallon, for a Toyota Camry traveling at a speed, my input is v miles per hour, right? So you can see slower speeds, we're not getting quite as good mileage, right? There's kind of a sweet spot here, somewhere in that 55-ish range, and then faster than that, our miles per gallon starts decreasing again. So we're going to take a look at the scatter plot of this data and make sure that we do think a quadratic model is a good choice. But even without looking at the scatter plot, we've already noticed that our m values, our outputs, are increasing here and decreasing there, which sort of indicates that parabolic shape, right? It's definitely not linear. Lines only go in one direction. Going up and then down again is a parabolic shape. And again, it's because the outputs both increase and decrease. But in addition to just sort of seeing that informally, let's do an actual scatter plot, and hopefully we'll see a pattern that suggests that a parabola would be a good choice so that we want a quadratic model. So I'm going to add my new table here, and my inputs are the speeds. Oops. $30 to $70, and I'll put in the fuel economies here. Give me just a moment. Okay. Now this is a terrible window. It almost looks like they're all 0 because I've got such large values here on my y-axis. So I definitely need to change that. There we go. It's a bit better. All right. So I'm definitely not expecting a perfect parabola, but going up and coming back down, we really only have 2 models to choose from at this point, linear and now quadratic, and this is certainly a much better model for quadratic. The pattern suggests quadratic rather than linear. So I'd now like to, this is part B, use technology to find the best fit model using function notation. Remember with a line, we just thought about y equals mx plus b? What does the equation for a parabola look like? Well, parabola in standard form is y equals ax squared plus bx plus c, right? So if I put that in Desmos notation, it'll have to be y1, and we always use the tilde to do regression when we want it to give us an equation. And then it'll have to be ax1 squared plus bx1 plus c. So think about what the equation should look like, and then just translate it into Desmos notation. And Desmos hopefully will give me the a, b, and c that I need. Let's try it out. And there we go. Again, Not bad, right? You can see the points are pretty close to the parabola that got drawn. The r squared is 0.93, so not super, super close, but really not bad. And indeed, they give me the a, the b, and the c values that I needed. So I'm going to jot those down, and then we'll go write our equation. I'm going to keep 3 decimal places. So a is negative 0.017. B is 1.905. And C, negative 24.864. So there's the A, B, and C values from Desmos. All I'm going to do now is write this with the function notation and the variables that were defined up here in my table. So instead of y, I want m as a function of v. And then I'm going to use the standard form, but again, instead of x's, I will have v's. So negative 0.017 v squared plus 1.905 v minus 24.864. All right, the next question is to find the zeros of this function, m of, whoops, that should say m of v, sorry about that, and explain how they relate to model breakdown in this situation. So if I come back over to here, I'm going to turn off the points again. Once I have my model, I'm going to answer all the questions based on the model. And let's see. The zeros, the x-intercepts, right, would be, let's see, for me it's not really x, it's v. So v equals 15.1 about, and v equals 96.9. And when that happens, notice the m values are the zeros. The outputs are the zeros. So this is really saying that if you go 15.1 miles per hour, you get 0 miles to the gallon. And the same if you're going about 97 miles per hour. Clearly that's model breakdown. You have to get at least some miles to the gallon. So that certainly relates to our model breakdown idea, but let's explain that. This says that at speeds of 15.1 miles per hour and 96.9 miles per hour, fuel economy is 0 miles per gallon. Oops, can't write all of a sudden. 0 miles per gallon. Get my abbreviations messed up here. This is certainly model breakdown. You certainly can drive 15 miles an hour and manage to go on less than infinitely amount of gas. Infinitely much gas. So this is clearly model breakdown. I might also mention that anything slower than our, what was it, 15? And anything faster than our 97 predicts negative gas mileage, which is also clearly model breakdown. So if we wanted to add that, we could. So also for speeds less than 15 miles per hour and more than 97 miles per hour, we get model breakdown. All right, at what speed does the Camry get the best fuel economy? The best fuel economy is going to be the most, right? You want the most miles per gallon. And the most, or maximum, is going to be that vertex again. So if I come back to my model, The vertex from the graph is 55, well, just about 56, actually, if I round to the nearest tenth, comma 28.4. So, according to the model, we get the best fuel economy at 56 miles per hour with 28.4 miles to the gallon. At 28.4, sorry, miles per gallon. Now, if you're thinking, wait a minute, I remember the chart here, and that was, we did better than that, right? We had 30 miles to the gallon here at 55 miles per hour. And what I need to remind you is at this stage of the game, we are making predictions according to our model. Our model is our regression equation. So our regression equation has a maximum at 56, 28.4. Therefore, according to the model, the best fuel economy happens at 56 miles per hour. Okay? If you remember, when we looked at our model originally and I had the points turned on, the actual maximum point was one that missed the parabolic model by a fair amount here, right? The actual maximum point was a bit above the parabola, the model that we got. So it's not surprising that the predicted maximum is actually a bit short of the true maximum according to the data. And that happens. Just remember when you're answering these questions, according to the model, you answer them based on the graph of the model, not based on the original data in the chart. All right, and then finally we wanted to find the interval of increase for this model and describe what this would tell someone driving the car. So again, we had our turn off the points and just look at the model. There's our maximum. This model is increasing until we get to the maximum. So it's increasing for inputs or V values less than about 56. So from negative infinity to 56 is our interval of increase. What does that mean for someone driving this car? Well, we're not going to worry too much about the negative speeds, but no matter how fast they're going, if they're going less than 56 miles an hour, they'll actually improve their fuel economy by going faster. So if you're driving slower than 56 miles per hour, fuel economy will improve if you speed up. Of course, the flip side of that is if you're going more than 56 miles an hour, your fuel economy will actually get worse. We go back down, or we get an interval of decrease right past 56. But if you're going less than 56, you'll actually do better on your fuel gas mileage if you go a little bit faster. All right, we have one more, I believe. In example 5, one source of renewable energy is wind-generated energy. And the table here gives us the cost per kilowatt hour of wind energy in different years. And you can see, like with most new technologies, right, it started out higher. As the technology improved and we got more efficient, the cost per kilowatt hour got lower and lower. And then in 2008, it actually started going up again a little bit. So we have a long decline or decrease, and then a little bit of an increase at the end. Since we do have both decrease and increase, though, it would make sense that to model this well, we're probably going to need to use a quadratic function, not a linear one. So, if I want to find a function that models the data, I'm going to go ahead and do a quadratic regression. Let's start with that, and then we'll write it down with our variables when we're ready. So I'm going to put a new table here. And, oh, did they tell me the years? They did not, so I'm going to assume that we can start with 1980. So let's go ahead and for a t value here, let's let t be the years after 1980. And then I'll go with p for price. Per kilowatt hour, and this actually is in cents. I don't think I indicated that in the chart, although it's, if you look at the graph at the bottom of the page, it's clearly cents. So, putting this data in, t equals 0 is 1980, so we would then have 4, 8, 12, 16, 20, 24, and 28. It goes every 4 years. And I'm going to put the prices per kilowatt hour of wind energy. All right, and I'm going to do a zoom fit on this. There we go. So you can see this actually looks pretty nice, doesn't it? It looks very much parabola-like. Now, of course, if it's truly a parabola, it would keep on going up, and we'll have to see if that's true. But for this, it looks very much like a piece of a parabola. So I think my quadratic regression is going to go very well this time. So y1 tilde, and then it's the expanded or standard form of a quadratic, ax1 squared plus bx1 plus c. And indeed, you can see that the points are very close to the graph, to the model. The r squared is 0.998, super close to 1, so really good fit. And then we're given the a, b, and c values here. So I'm just going to jot down the a, b, and c values, and then we can write the model in a minute. A is 0.112, again I'm using 3 decimal places. B is negative 4.818. And C is 55.083. All right, so mine is going to be a P of t with my variables. And that'll be 0.112 t squared minus 4.818 t plus 55.083. So the next question is, let's predict the price in 1990 according to our model. Right? So let's see, since our model had 0 as the year 1980, what we're really looking for here is P of 10. Now I'll mention, really it doesn't matter. If you had to find a whole bunch of prices, I'd for sure want to put this function in function notation. In this case, we only have to do it once, so it's kind of your call. But what we have right now is not yet written in function notation. So if I want to be able to use that, I would have to put that in myself. And by the way, you can always check your typing. Notice how the original that they graphed and the red is what I've graphed, and they're right on top of each other, so I must have hit all the right keys. There's just a tiny discrepancy over here. That's because I rounded off my values. If you have much discrepancy, it may be that you've rounded off too much. Definitely recommend keeping at least 3 decimal places in these regressions. All right, so 1990, we said we wanted P of 10. 10 years after 1980. And there it is, about 18.1. And this was in cents per kilowatt hour. If you look up, 1990 here is between 1988 and 1992, and that 18 cents is right in there, so it certainly seems reasonable. All right, next we want to find the vertex of the model and explain what that means. So I'm going to turn off theirs and just keep mine. And I'm going to turn off the points as well. And then I can kind of see a little bit easier. There it is. The vertex is about 21.5, comma 3.27. Now this vertex is a minimum. So with my input being time, I would be during the 21st year, right? 1980 plus 21, so during 2001. We hit the lowest price of about 3.3 cents per kilowatt hour. So the minimum price of about 3.3 cents per kilowatt hour happened during the year, when you add this to 1980, the year 2001. All right. This is actually the source data that I used for you. And the bar graph here shows us that our data for cost of wind energy over time. Based on what we see in this bar graph, when do you think our model that we found up here is probably going to break down? Well, what I see here is this seems to follow a reasonable parabola for a while, but then somewhere right around in here, right, we start having a problem because now it starts coming down again, which a parabola would not do. So I would suggest that somewhere, it looks like that's between 2008 and 2009, it was still going up. So I'm going to say right around 2009 is probably the last year that I would want to think my model is any good. By 2010, we probably are experiencing model breakdown because we're starting to see a decline in price again. So the model will break down after 2009. By 2010, prices are decreasing again. Whereas our model would, of course, just keep increasing because we're in the increasing part of the parabola at that point. All right. The very last question asks us to address that last little piece of the data. It says, using that graph that we just were looking at, could we find a piecewise function that would extend the useful life of our model? Well, if we assume that we're okay through 2009, which is where our graph stopped increasing. Whoops, I'm sorry, I don't have that where you can see it. There we go. So if we assume we're okay through 2009, which is where our graph stopped increasing, let's look at what happens in 2010 and beyond. Look at the pattern here. It's very short, but would you agree with me that it looks pretty linear at that point? I feel like we could probably use, let me find a different color here. Here we go. I feel like we could probably use a linear model for this part. we already have a quadratic model that had fit this part very well. So, thinking in terms of our variables, again, our t-values were years after 1980. So 2009, that would be the 29th year. So we'll use a quadratic model for t's from 0 to 29. And then we're going to want to use a linear model starting in the 30th year after 1980. That would be 2010. And we only can really predict out through the 33rd year because that's all the data we have. So I'm going to set up my two pieces with those two domain elements in them. So let's write down what we know right now. Our model P of t. We already have the quadratic model, right? We already figured that out. So I'm just going to copy that from here. It was 0.112 t squared minus 4.818 t plus 55.083. And as we just said, we only want to use that for t-values between 0 and 29. Now the linear model I still have to work on. So to get this linear piece, let's make a new table of values for ourselves. And this will be for 2010, which is going to be our t equal 30. 2011 will be 31. 2012, 32. And the last year we have, 2013, will be 33. And I am going to have to do a little bit of estimating here. So let's see. 2010. This actually tells us that we go down to 2.2 or 2.5 cents here at the very end. So let me actually start with this. 2.5 cents per kilowatt hour. That's all the way at the end there in 2013. And looking at this, let's see. This is 10 right here, right? So I'm going to say this value in 2010 looks to me like it might be about 7. Let's try 7. And 2011, maybe about 5. No, maybe 6. It looks like it's a little bit past halfway between the 0 and the 10 there. And then in 2012, I'm thinking it's a little bit below the halfway point between the 0 and the 10, so I'm going to call that 4. Okay. Again, we're doing our very best to estimate, but we know these values aren't precise because I don't actually have the specific source data for that. But they seem reasonable based on my estimates from the graph. All right, we are going to do linear regression on this. So y1 tilde mx1 plus b. So I'm going to make a new table. My inputs are 30, 31, 32, and 33. And then my estimated prices here. Not bad, it looks reasonably linear. And notice this is an x2 and a y2, so actually I should have done that over here. I was using a second table, so my regression will have to be y2 and x2 when I do this. There we go. And looking over here where I actually have the points, again, the points are really close to the line, so I feel like it's a pretty good fit. My r squared, 0.985, great r squared, and there's the slope and the y-intercept. So the m, negative 1.55, and the b, 53.7. So, putting this into my notation, my p of t will be negative 1.55 t plus 53.7. And that should be, again, for the t values, just from 30 to 33. If I want to put all of that together and see it in a graph to see if the shape resembles the graph on page 110 of your course pack, I'm going to get rid of all this mess and I'm just going to start fresh making a graph. I'm going to say I want to graph, let's just do y equals 0.112 t squared minus 4.818 t plus 55.083, but only as t's are between 0 and 29. And then I want to graph y equals, and let's see, I would have negative 1.55 t plus 53.7, but only for t's between 30 and 33. All right, now I don't have a very good scale here, so let's see if I can, there we go, make this show up. And there we go. We have the parabolic part of the graph, and then we have the little linear piece. They may not fit together perfectly, but actually if I changed the second piece and kind of tried to pick it up where I left off at 29, I bet you they'll come close. Yeah, they come pretty darn close to meeting, right? So it wouldn't hurt to do that. The 29th year is pretty well predicted by either the parabola or the line, so I could do it that way as well. All right, so that puts our piecewise functions in perspective. You can have two parabolic pieces, you could have two linear pieces, you can have a parabola and a linear piece. Piecewise functions are made up to suit the data that they're meant to represent. All right, that is the end of section 3.5.